Yes. So example 6. It says to create a MacDaddy series for sine of x squared. Find the first 4 non-zero terms in the general term. So the first thing you're going to read is Maclaurin, and that means that it's going to be centered where? At 0. And since the ones we memorized were centered at 0, we do not have to reinvent this series. We can just modify the existing one. So you got to be real careful when you're creating series. I would always recommend write down the original series and then build the new one line by line. So it's also good to write it down because it kind of reinforces it. So sine of x is, of course, what to start with? X, right? X. So x plus, you say? That's a positive term. So the next negative, x cubed over 3 factorial plus x to the 5th over 5 factorial. Now it says find the first 4 non-zero terms. So instead of giving you like the degree, they'll typically say how many terms. So that's 1, 2, 3. I need one more. So that's minus x to the 7 factorial plus, did it say the general term? Yes. Now that you want to read very carefully because sometimes on the free response, it doesn't say give the general term. So you don't want to volunteer it if you don't have to because you could only lose points if you have it there and it's wrong. But most of the time they do say to put it. So plus, dot, 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 plus, and remember for sine, it's a negative 1 to the something, and then it's x to the 2n plus 1, 2n plus 1 factorial, and then plus dot, 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 and then was it n or n plus 1? N. Yeah, because in this case we start at 0, it gives us x to the first, and negative 1 to the 0 is positive. So now that we have that, we can create sine of x squared. Because the center is the same, we could just adjust this one, and we get x squared minus, if you want to simplify as you write it in there, that's fine. X squared cubed is x to the 6. So very, very similar to what we did with Taylor polynomials. It's just we have plus dot, dot, dot instead of stopping. We have equals instead of squiggles, and here we have the general term. That would be x to the 10th over 5 factorial minus x to the 14th over 7 factorial plus dot, dot, dot. So here's why knowing the general term is helpful. If you didn't know the general term, you would probably then have to reinvent the pattern for this new series sine of x squared, which maybe you could handle, but it's easier to memorize the original one and just modify it in much the same way. It's going to be negative 1 to the n, and we're going to replace x with x squared. So when you raise a power to a power, you multiply. So it'll be x to the 4n plus 2. Excellent. 4n plus 2 all over 2n plus 1 factorial plus dot, dot, dot. There you go. So that easy. You modify the general term like you would each individual term. And that would probably be worth 2 points on a free response right there. Not bad at all. All right, example 7. Find a Maclaurin series for g of x equals x cosine of x. Again, first 4 non-zero terms. So in this case, instead of substituting in for x, we're going to multiply through by x, very similar to the polynomials again. So x cosine of x, well, we don't do that first. We're going to build it off of which one? Cosine, makes sense. So cosine of x is 1 minus, they alternate, yeah, 2 factorial plus x to the 4th, 4 factorial, minus x to the 6th, or 6 factorial. So those are the first 4 non-zero terms. So again, the way you write the general term is you put plus, whether it's negative or positive, plus dot, 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 plus, then the nth term, which is negative 1 to the n, x to the 2n, quantity 2n, factorial, and then after that you put plus dot, dot, dot again. So you're kind of saying somewhere down the line, you have the general term, and then after that it keeps going forever. All right, so now we'll just put x cosine of x, and now we'll just multiply everything through by an x. We'll distribute. So we get an x minus x cubed over 2 factorial plus x to the 5th, 4 factorial minus x to the 7th, 6 factorial plus yada, 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 plus, and then again, just as easy here, negative 1 to the n, and now we're going to multiply by x. So x to the 2n times x to the first. What do we do with the exponents? We add 1. Yeah, 2n plus 1. And just make sure that it's in exponent land and doesn't fall down. All over still 2 times n factorial plus dot, dot, dot. Sweet. All right, and then we're moving fast. Example 8. Find the Maclaurin series for this one. So this one's a little bit more work. E to the x plus e to the negative x over 2. This is actually called, this is the function known as cos of x. Y'all ever seen that one? It looks a whole lot like what? Cosine of x with an h. And it is. We call this the cos, yeah, it's fun to say cos of x. This is called hyperbolic cosine. Hyperbolic cosine. And it's defined to be e to the x plus e to the negative x over 2. Okay, a catenary curve takes on a hyperbolic trig function shape. A catenary curve is kind of like a parabola, but it's the shape that you would get if you suspended a chain and you let gravity kind of do its work in the sag. It would take the shape of a catenary, not a parabola. So the Gateway Arch in St. Louis, it's the most famously mistaken. People mistake it for a parabola. It's actually a catenary. But anyway, we want to develop a polynomial for this. So to do that, we're going to build it off of e to the x. Yeah, good choice. So here's e to the x. Let's go ahead and write it out. That's the easy one, right? 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Those are the first 4 non-zero terms. So then plus dot, 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 plus it's x to the n over n factorial plus dot, dot, dot. Now underneath there, let's go ahead and create e to the negative x. So we're just going to now, it's not all negative. We're not distributing a negative through. We're just replacing x with negative, right? So we get 1 minus x. What happens on the next term when I square a negative x? It stays positive. Yeah, so now plus x squared over 2 factorial. The odd powers are going to become negative essentially, and the even powers become or stay positive. Now, if you wanted to do the general term, you could do it as negative x quantity to the nth power over n factorial. That would be fine. But remember what I told y'all yesterday, this now is going to be a combination alternator and magnitude generator. So you might want to separate that. So negative x quantity to the n is the same as negative 1 to the n times x to the n. But you wouldn't necessarily have to separate them to get credit. You're just modifying the original one. But the parentheses would be important. So that's pretty cool. It becomes now an alternating series. Now, notice the numerator requires me to add these together. We haven't done that yet. So how do we add one infinite series to another? Very carefully. Vertically will be nice. Vertically works great. So if I add vertically on the left, I get e to the x plus e to the negative x. And on the right, I get 1 plus 1 is 2. What happens with the next terms? They cancel, right? And the next ones are going to double. So I have plus, and I'll do this one in baby steps. I get 2x squared over 2 factorial. And then the next ones cancel out. Now, here's the problem. It tells me that in the very end, I need to have the first 4 non-zero terms. I thought it was good just generating first 4 non-zero terms for each of them, but now every other one of them canceled out. So now I only have the first 2 non-zero terms. Can we predict what the next one would be? Plus 2x to the 4th over 4 factorial, and then plus 2x to the 6th. Good. So this is where picking up again on the inherent pattern of the new series that you're creating can help you generate terms without having to either expand the originals or, regenerate them with Taylor's rule. And then plus dot, dot, dot. I will need the nth term. So how can I add these together? Well, here's where you want to do a little bit of looking or thinking. Notice that the only terms that are left are the positive terms. So the alternator is going to go away, right? So it looks like at least the powers and the exponents are the same. So x to the 2n all over 2n factorial. 2x to the n. Yeah, there'll be a 2 up front, definitely. Yeah, the 2 is part of it, the problem. And then, will the 2 to the n generate the powers? When n is 0, I get x to the 0, so that would work there. When n is 1, I get x squared. When n is 2, I get x to the 4th. So it should work like that. And then plus dot, dot, dot. And now the last thing I need to do is divide everything by 2. So that's the same thing as multiplying everything through by what? 1/2. So that's what I'll do. I'll multiply everything through on the right by 1/2. And, oh boy, this would be fun. What happens with all the 2's now? They become 1's, right? So I have 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial plus x to the 6th over 6 factorial plus yada, yada, yada plus x to the 2n over 2n factorial plus et cetera, et cetera, et cetera. Now that series looks a whole heck of a lot like which one that we've memorized. It looks a lot like cosine, except cosine alternates, right? This one does not alternate. They're all positive. So because it's related to cosine in the series, that's why this also has a separate name. It's the hyperbolic cosine. And the graph looks like the graph of e to the x plus e to the negative x, but you could graph this easily on your calculator. There's a hyperbolic sine. There's a whole set of hyperbolic trig functions. Yeah. Okay, so just kind of an interesting thing. We had to generate extra terms because half of them canceled out. But that was not a big deal. Okay, now for the last one. Well, at least I wanted to make sure I got this. We may roll into the next section. Using known Maclaurin series, prove this is Euler's identity. And to me, this is one of the most beautiful equations ever to be invented or discovered? What would be the right word? Discovered. Yeah. This would have existed whether or not Euler tripped over it or not. Okay? Now, the reason it's so beautiful is, first of all, it's true. Right? The left side does equal the right side. So it's not lying when it says equal to. It's very concise. Right? It's not too elaborate, so it's simple. And simple things are inherently beautiful. And it also has all of the building blocks of really all the mathematical branches. It has addition in it. See that? Addition, which is really subtraction as well, right? It has multiplication in it, pi times I, and it has exponentiation. So it has the three operations going up the operational ladder: addition, multiplication, exponentiation. It also has 1, the identity element of multiplication. It has 0, the identity element of addition. It has, of course, the two most famous irrational numbers in all of mathematics: pi, the geometry irrational number, and e, the analysis number or the calculus number. And then it, of course, has I, the imaginary unit, which is the square root of -1. So all contained in one tiny little equation. It's beautiful. Now, some people have then used the very existence of this equation to prove the existence of a divine being. For this thing could not have existed without some divine equation maker. Okay? It's called the teleological proof of big G, not little g. Okay? If you take Philosophy 101 in college, one of the things that all philosophy students study is all the different proofs for the existence of God. Descartes was the ontological, I think, therefore I am. This is the intelligent design argument, okay? Like the watch on my hand had to have a watchmaker. There is no way that this watch on my wrist could have just come together by some random assembly of parts that just fell into this configuration. Wow! How random is that? Highly unlikely. So by that argument, then, same thing goes with the equation, all right? So whether you believe in that or not, That's up to you, but the equation itself is beautiful. So let's see why it's true. We can use series for that. I'm going to start with the exponential function e to the x, and of course its series is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. I'm going to go out a little bit further here. 5 factorial, and you'll see why, plus x to the 6th, 6 factorial, plus dot, dot, dot. I'm not going to use the nth term here. Bless you. It's not going to be necessary. Bless you, bless you. All right, so now one of the things we know we could do is we could substitute. So what I'm going to do is I'm going to change this from e to the x. I'm going to substitute in an ix. So I'm going to replace x with I times x. All right, so real quickly off to the side here, let's review. I is I. It's the square root of negative 1. I squared is negative 1. I cubed is negative I. I to the 4th is positive 1. And then it repeats, okay? I to the 5th is the same as I, bless you. I to the 6th is the same as I squared, which is negative 1. So they keep repeating. All right, so if I do that and simplify as we go, let's see what we get. We get 1, and then I get plus ix. Sweet. Now, if I plug it in here, what is ix quantity squared? It's I squared x squared. But what is I squared? Negative 1. So this becomes minus x squared over 2 factorial. If I plug ix in here and cube it, I get I cubed x cubed. But I cubed is negative I. So this becomes negative I x cubed over 3 factorial. I x to the 4th is I to the 4th x to the 4th. I to the 4th is 1. So this becomes just x to the 4th over 4 factorial. And then we kind of start over again. I x to the 5th is I to the 5th. Well, I to the 5th is I. So it becomes plus I x to the 5th over 5 factorial. I to the 6th is the same as I squared, which is negative 1. So it becomes minus x to the 6th over 6 factorial. So on and so forth on down the line. So here's what I'm going to do now. It seems like I have some terms that have I in them and some terms that do not have I in them, like team. Okay? Let's go ahead and group the I terms and the non-I terms together. The non-highlighted ones, I'll write those first. It's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus yada, yada, yada. There's infinitely more of those, right? Plus, everything that's highlighted has an I in it, so I can factor an I out. Yeah, yeah? Let us factor an I out then. I parentheses, and now we're left with x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus yada, yada, yada. Okay? So here we go. We now have e to the ix. Let me rewrite that. E to the I times x is equal to, yeah, you recognize some things, don't you? What is this whole thing actually equal to? That one is cosine. That's cosine, exactly. It's cosine. Cosine of x. And then plus I times, what is this one? Sine. Oh, wow. This is an important result of Euler as well. And that's cool right there, because that relates e to a sine and cosine function. Wow. Okay? And now that we have this function of x in non-power series format, we can evaluate it at pi. So now I'm just going to go ahead and say when x equals pi, let's plug in. And I get e to the I pi, which is also e to the pi I. Multiplication is still commutative. If you do a Google search for Euler's identity, you'll see e to the I pi. But I never like to put myself first. I like e to the pi I. I think it sounds better. E to the pi I. It almost sounds like p pi. Pi. Right? E to the pi. Did you say pi or pi I? Pi. Maybe that's why they say I pi. Anyway, let's plug it in. I get cosine of pi plus I times sine of pi. And even in Euler's world, guess what time it was at this time? Unit circle. Pi 30. It's unit circle time. All right, so I get e to the pi. What's cosine of pi? -1. And what is sine of pi? 0. What's 0 times I? It's 0. It's still 0. So you know with e to the pi I equals -1. And then you just add 1 to both sides, and you get e to the pi I plus 1 equals 0. Done. It's beautiful. Yeah. That is beautiful. If I had a bigger forehead, I might get all of that tattooed up here. You know? Yeah. But e to the pi I plus 1. Pretty neat. Very neat. So if you're into that stuff, teleological, kind of interesting. Proof by design, intelligent design proof, essentially. So there you go. There is Taylor series, Maclaurin series, and you got to memorize the 4 really: sine, cosine, e, and then 1 over 1 minus x, which the whole next section's about. We're getting closer. There's only 2 sections left this year. Only 2. Any questions so far for the whole year? What's the magic number when you're taking volumes of solids whose cross sections are semicircles? What's the magic number? Pi 8. Good. You still know that. Good. That's just a random quiz. All right. Kind of stop the recording here.